Okay, question number 11. A wire has a resistance of 65 ohms. The length of the wire is 0.25 meters. The wire has a circular cross-sectional area. Calculate the diameter of the wire. Resistivity is this much. So just write down the formula for the resistivity and the length in the area, and they're asking you to find out the diameter. For that, first of all, you need to calculate the area. Okay, and you are going to have areas by r square. So uh, yeah, this is going to have the under root. So r is just putting down the values. So r is resistivity is this much. Rho is that resistivity 5.6 into 10 raised to the power minus 8. Length is 0.25 pi as it is into r is resistance, which is 65 into 10 raised to the power minus 3. Okay, so with this in mind, you just do the 2r equals 2 times of the answer. Okay, let me calculate that first. That's 5.23 into 10 raised to the power minus 4. Okay. Now you need to see that there are two significant figures in your given data. So your answer should not be in three significant figures, not allowed. If that is the case, you will get just 3 marks in this question, not 2 marks. Okay. If this question is 2 marks, you will just get 1 mark. So the number of significant figures in the data set and in your answer should be same. For example, you have variable number of significant figures. One is 1, one is 2, one is 3 in the data. So you need to write your answer in the minimum number of significant figures, okay? So therefore, your answer is going to be simply 5.2 into 10 raised to the power minus 4 meters. I need to see the mark scheme for that for confirmation. Please hold on. Yeah, exactly. It is 5.2 into 10 raised to the minus 4. And you can see that in the answer they have calculated this, but in the answer they're not writing this, and they're saying exclusively that 1 mark is for writing it in appropriate number of significant figures. Okay. A student uses a ray box to direct narrow ray of light onto the surface of a glass block. Determine the angle of incidence. So in order to find out the angle of incidence, you just need your protractor. Okay. And using your protractor, first of all, you will make a perpendicular line here like this. Okay. And just place your protractor here like this. This will be your 0. Okay. Just keep your protractor like that. So you will, for example, it is 0 and it will be, say, it will be somewhere, as mark scheme says, it will be somewhere 53 to 55. So this will be your 53 degrees. That will be your angle of incidence. Okay. So calculate the angle of refraction in the glass block. So angle of refraction means that the light is coming and going and like bent towards normal, because The glass surface is denser than the air, so it will be moving like that. And this is the angle of refraction that you need to find. So just use n1 sine theta incidence equal n2 sine theta refraction. So this is also the first material, no matter it is denser or lighter, and it is the second one. Just follow where the light is going, from denser to rare or rare to denser. If the light is moving from rare to denser, I mean light denser to the more denser, it means the light denser is first and one, and the more denser is second and two. And if the light is moving from denser to the lighter one, then denser one is the first one and one, and the lighter one is the second one and two. So for air, we know that the refractive index is 1, and sine 53 degrees that we have just calculated. And 2 is for glass, it's mentioned 1.5, and angle of refraction is something that we need to find. And when we do the calculations, our answer is acceptable anywhere between 32 to 33 degrees. So you can do it and check your answer. Okay, B part. The light from the ray box is unpolarized. When reflected by the glass, some of this light will become polarized. Okay, explain the difference between unpolarized light and the polarized light. Well, the unpolarized light travels in all directions or all planes. You just write unpolarized light moves or has oscillations. This is the keyword by Edexcel, so I'm going to write the keyword has oscillations. Edexcel love to hear this, has oscillations in all directions or planes. Okay. And the best example of this is like your ordinary light bulb or anything. So it moves in all directions, but the polarized light has oscillations in one plane. Okay. And what really important that you need to write for the third one is that the oscillations will be perpendicular to the direction of the wave. For example, if the wave was moving this way, the oscillation will be like this, up and down. Okay. So if the wave is traveling this way, direction of wave, and the oscillations will be up and down, direction of oscillation. So this was unpolarized, and polarized light is only having this much. So it is a sort of laser, you can say. Okay. And it is kind of an ordinary light. I'm just trying to explain you what is the difference between laser and ordinary light. So you can easily see there is a big difference between ordinary light, which moves or spread out in all the directions, whereas the laser only travels in a specific direction. So ordinary light is kind of unpolarized light, whereas the laser is polarized one. So here you can see that the direction of the oscillation is perpendicular to the direction of wave. So you just need to write that the light, the electric field, this electric field is having is spreading out in all the direction. It's like spreading out in 360. and that is for unpolarized light. Okay, but when we polarize it, we have the direction and the electric field there still, but now the electric field is not moving 360, it is only traveling specific in a specific plane. Just remember this. Okay, that is the difference between the polarized light and the unpolarized light. PL means polarized light and UPL means unpolarized light. So if we say that uh, you need to remember that what do we mean by vertically polarized and what do we mean by horizontally polarized. So actually it depends uh, on the direction of the electric field. Okay, 3 points, but everything else is the side knowledge just for your concept to get cleared about polarization. Okay, the student uses a polarizing filter to view the light reflected by the glass block. Okay. Explain what she would observe as she rotates the filter. Mhm. So here's the block. Here was the light coming up. Okay. And there was a normal. And there was some light moving down. And there was some light moving in this direction as well. So light also reflects and reflect. Okay. Now here there is a kind of now there is a student. This is a polarizing filter. Okay. This is polarizing filter of the student. Okay. And this is the reflected light. Okay. And is there anything else that you have mentioned? The light beam from the X-ray box, when the reflected by glass, some of this. Okay, yeah, this is the point. So they're saying when the light is reflected from the glass, it is polarized. So that is another key information that you need to remember. Okay. So here is your figure, and the reflected light that is coming here is now polarized. What does it mean? It means the light which was coming from here was like this, moving in all directions. But now the light which is coming here is only having the oscillation in one plane. Okay. So this is the light coming. So you know that intensity, and this is angle of rotation of the polarizer. Okay. Angle of rotation of polarizing filter. So say that the light that is coming here is now having the intensity I naught, but here your angle of rotation is 0 degree at the moment. So what intensity you will receive here? So the student which is looking at this light through this eye will get how much of the intensity. This is what we need to find. So for this, just refer to the same formula, I equals I naught cos 0 degree, because we have not rotated it so far. So cos zero's value is h square. So I equals I naught into 1, and you can see that the intensity will remain as it is. So we will say that the maximum intensity will be maximum intensity of light will be observed when light and polarizing filter are at 0 degree. Okay. So they were asking you to explain how it is going to expert. So this is the point number 1. And for point number 2, as theta is increasing, so up to 90 degree, the intensity the intensity will decrease. Okay. Why is it so? Because again, I equals I naught cos theta. So when theta is increasing, actually cos theta decreases, because cos 0 degree is 1, but cos 90 is 0. What does it mean? You're rising the theta from 0 to 90, and cos theta is decreasing from 1 to 0. So therefore, the second point that you have to write, first point is maximum intensity will be observed when there is an angle 0 degree between the incident light and the polarizing filter. The second point is as the student is rotating, as theta increased, because student is rotating the polarizing filter PF, okay? Then the intensity will decrease because I equals I naught cos theta square. So just put here I equals I naught cos 90 square, and cos 90 is actually 0, okay? Zero. So I equals 0. So the intensity will become minimum at 90. So you just write the third point as the intensity is 0 at 90 degree. And what is the angle 90? 90 degrees, the angle between the incident light and the polarizing filter. Okay. I hope you understand the concept of this polarizing filter. 13. Concrete is often used in building construction. After several years, concrete may develop cracks. Ultrasound can be used to find these cracks. A transducer sends pulses of ultrasound into a piece of concrete as shown. So you may wonder, or you may have seen transducer in the hospitals when we go for the ultrasound. So transducer is actually a sum of two words, transmitter and receiver, okay? Transmitter and receiver. So when we shortify that, it becomes transducer. So it means it sends and also receives the signal. So for example, send signal is 10 joule and the receive signal is 6 joule. It analyzes the energy difference and it analyzes the wavelength difference. So for example, here it is 15 and here it is 12. So by analyzing the wavelength and the energy, it explains the location for the crack. Okay, right. So there is something very much important you need to remember regarding the ultrasound, and this is this one. The, the transducer detects pulses of ultrasound reflected from the crack. So these are the reflected ones, and these are the incident ones. Okay. To be detected, this is very much important. very, very important that you have to remember. To be detected, the wave, the reflected pulse must not overlap with the pulse emitted by the transducer. What does that mean? That means that if the transducer is sending one pulse, like uh, in 2 seconds, it sends one pulse. So after 4 seconds, it will have another pulse, right? And after 6 seconds, it will have another pulse. So all these are the incident ones. So the wave which is coming up again here is also received and analyzed by the transducer. So just take an example. If the transducer is emitting a wave which is taking up to 2 seconds, it takes 2 seconds to completely transmit one wave. And within that 2 seconds, if another wave arrived, reflected wave arrived in less than 2 seconds, what will happen? So reflected back is arrived back at transducer in 1.5 seconds. Okay, say that in 1.5 seconds, the the reflected ray is arrived in 1.5 seconds. So do you think there will no collision, or there will be collision between the incident and the transmitted? Because at that time, the transmitter will keep on transmitting another signal, because it takes 2 seconds, fully 2 seconds, full 2 seconds for the transducer to transmit successfully one signal. And at the same time, in less than that time in which it was transmitting, the reflected ray is arrived from the crack. Okay, so it means that this information will not be analyzed to read by transducer. Okay, so you have to be very much careful with this information. Now, in this piece of concrete, the speed v of the ultrasound varies with temperature as shown. Okay, very good. So giving you this background of the question, now going back to the question, you have this question and they're saying the transducer to be detected, the reflected pulse must not overlap with the pulse emitted by the transducer. In this piece of concrete, which is shown here, this piece of concrete, the speed v of the ultrasound varies with temperature. Okay, as you are rising the temperature, the speed is also increasing. As you can see the straight line graph, a pulse of ultrasound is incident on a crack in a piece of concrete. The crack is at a distance of 4 centimeters from the transducer. The temperature of the concrete is 23 degrees centigrade. Deduce whether the transducer can detect ultrasound reflected from this crack, and duration of the ultrasound pulse is 200 microsecond. Now I gave you an example of 2 seconds, but here they are mentioned that the transmitter is taking 200 microseconds to complete one wave. So uh, we need to first of all see at 23 degree what the graph is telling us the speed is. So at 2300 degrees centigrade, you just need to see the speed. So this is 2300 degrees centigrade, and so I believe it is going to be 4115, right? Yeah, I think it is 4115 meter per second. So the transducer. So if you see that this was the crack, and here we had the transducer. The light was sent like this, and this distance was 4 centimeter. So this is in and this is out, or reflected one. This is incident and this is the reflected. So it means the speed of the sound is actually equal to the total distance divided by time. And the total distance is actually 4 centimeter plus 4 centimeter divided by time, which is given here as the time that actually we need to find, sorry. So T is 8 into 10 raised to the power minus 2, because we have to convert that into meters, and V is 4115, correct? So the time that we are calculating from here is 19.4 into 10 raised to the power 6. So that means it is 19 microsecond, because 10 raised to the power 6 is this much. So it means that the incident wave will take 200 microseconds to get complete, but the reflected wave, uh, the reflected ray is coming out in just 19 microseconds. So the incident ray was taking 200 microseconds to finish, okay? And before the incident ray finishes, reflected ray in just 19 microsecond arrived, okay? So what will happen? Overlapping happened. And we will not be able to see the crack, okay? So crack will not be detected. So that was a rough answer that I have explained you. Now in a proper way, you need to write everything in here. Okay. First of all, you get this all in here, okay? That is the required explanation. So it will be like considered as one of the points, like there are 4 points. And then these two will be, yeah. Yeah, so this is the second point, this is the third point, and this is the fourth one in the end. And the fourth point is simply this one, okay? So this is how you need to write the answer in the exam for these 4 marks, okay? But I took some time to explain that. Okay. Pulses of ultrasound with higher frequencies can be used to find cracks of shorter length. Okay, so shorter line means good resolutions. For example, if I give you an example that this is a big picture and you just want to see by zooming in this dot. So you have to use a camera with a very nice resolution, okay, very high quality. Similarly, ultrasound is like a camera, so it detects and find out the cracks. So if you use a high frequency, you know that the frequency is actually directly proportional to the energy for the photons, and ultrasounds are photons, right? So if you increase the frequency, you are actually increasing the energy. So higher energy ultrasound waves will be able to detect smaller cracks. Okay. So what you need to write in here, you need to write that when F is high, energy is high. Ultrasound is also high. Okay. And when energy is high, you just write E equal HF, and HF is Hc over lambda. So from here, E is 1 over this. So you can easily see that it is inversely right. So it was not the second point, by the way, it was just the first point. Okay, we don't need that. So we just write that ultrasound waves will have better or higher resolution. So more likely to find the crack. Okay. Question number 14. The photograph shows an electric bicycle. The battery contains several identical cells connected in series. Each cell has an EMF of 1.5 volts. One cell is removed from the battery and connected in the circuit shown. When the resistance of the variable resistor is 10 ohms. Okay, let me write the data. This is 10 ohm and this is 1.4 volts. The reading on the voltmeter is 1.4 volts. Oh, sorry. This is 1.4 volts and this is 1.5 volts. Okay, calculate the internal resistance of the cell. Well, I can make this circuit like this. Okay, so this is my internal resistance. This is my 1.5 volts and this is 10 ohms and the voltmeter is showing out to be 1.4 volts. It means there is 1.4 volt here. So we can use we can solve this circuit using two methods. One is a potential divider and the other one is like a typical method to find out V and IR. So I will explain you in both ways. So which whatever you like easy to use, you can use it. So first of all, I'm going to solve it method one, which is potential divider way. So for this, you need to remember this equation: small v over capital V equals small r over capital R. Small v is always for the chosen component and the small r is the resistance of the chosen component, and the V is the total voltage of your circuit and R is the total resistance of the circuit. Okay. Now my chosen component is this one. Okay. You can choose any of the component of the circuit. Okay. Any component. You can even use a small resistor. You can even use a small resistance R. No worries. So my chosen component is small v, the variable resistor, and for that my voltage is 1.4, and the total voltage of the circuit is 1.5 equals, and for my chosen component the resistance is 10, and the total resistance should be 10 plus R, right? Because there is a small internal resistance in the circuit, and the resistance of our variable resistor is 10. So from here, you just do the cross multiplication, 1.4 R plus 10 equals 1.5 into 10, correct? And when you find out the internal resistance from here, it is going to be 0.71 ohms, or just rounded off to 0.7. No, I think 0.71 is fine because there are two significant figures. So 0.71 is going to find, because in the 0.71 we also have two significant figures. So that is the method to find out the internal resistance using potential divider method. The other method is simply conventional method, which is like very much common. So in the conventional method, first of all, you have the voltage here as 1.4, and you have the resistance here as 10. So in series, you know current is same. So you just write I equals V over R. V was 1.4 and the R is 10. And from here, the answer is going to be 0.71 amperes. Okay. So just give me a second. I think it's 0.14. Just let me check. Yeah. So now you have the current. So you use the Ohm's law equation equals IR, and the R is the total resistance of the circuit, and the total resistance is 10 plus small r. So the total voltage is 1.5 equals I, which was you have obtained 0.14 into 10 plus R. Okay. So from here, 1.5 divided by 0.14 minus 10 equals R. So 1.5 divided by 0.14 minus 10, and it is going to be exactly 0.71 ohms R. Okay, so you can use any of the way, whatever you choose to solve. But personally, I really much like the potential divider way, because there's no concept of same constant, same resistance, parallel, series, or whatever. Okay. The battery, okay, the battery in an electric bicycle gets warm when the battery supplies power to the motor in the bicycle. Explain why the battery gets hot when the bicycle is going up the steep hill. Okay.
Uh,
Oh, I was writing and I didn't know that the video was paused. So actually, I paused it just for writing, but now it's okay. Okay, when you're actually moving up the hill, it means you need more energy, right? The bicycle is moving up the hills, right? So it need more energy. So follow the sequence of my points. When you're going up the hill, battery supplies more energy. because battery is the energy source. Since 1.5 is the total EMF of one cell, right? And the resistance of the circuit, which is 10 ohm, is also not changing because they are mentioned. So resistance is not changing as well, and the voltage is not changing as well. So how can you increase power or energy supply? So you can see that the power is actually voltage into current, and we are saying that the voltage is constant. So it means we cannot do anything with voltage. We just need to write, we just need to increase current. So if we increase the current, there is only way we can increase the power, okay? And the secondly, if you see power is voltage into current, and if you put voltage as I into R into I, so again, we are saying the resistance is constant. So when the resistance is constant, it means there is only one way to increase the power, which is actually by increasing the current, okay? So when we see the EMF equation is V plus IR. So this is actually the voltage of the internal resistance, small resistance, and Vt is the terminal voltage and E is the EMF. So when the current is increased, this whole factor, because I is increasing, then the whole factor IR is also going to increase. And when IR is increasing, it means voltage across internal resistance is also increasing, right? So we say that because there is a lot of voltage at a very small resistance, the resistance is just 0.71 and you're increasing the voltage considerably high. So because of that, a heating is produced. It is similar to the short circuit because if the wires are having current more than their capacity, they become hot and heated up and result in a short circuit and fire. So similarly, internal resistance is very, very small and you're moving up the hill, and because of the more energy supplied by the battery, the potential difference across the internal resistance becomes very much high. Because of that, it becomes heated and we observe heating up of the battery. Okay, so that is the answer, and these are the 4 points that you need to remember. The diagram shows apparatus used to demonstrate the diffraction of an electron beam in a school laboratory. A beam of electron is accelerated by a high potential difference towards the piece of the graphite. The graphite diffracts the electron beam, producing the diffraction pattern on the fluorescent screen. State what is meant by diffraction. When the light passes through some narrow gaps, it spreads out. Okay, that is called uh, diffraction. So you can write that in your own words. Okay. An electron is accelerated through a potential difference of 4.9 kilovolts. Show that the de Broglie wavelength for the electron is 1.80 Newton raised to the power minus 11. Very important question. This is electron, not photon. First of all, please be careful, okay? So you cannot use E equal HF because that is the energy of the photon, not electron. Okay, so first of all, you're going to write voltage equals work done per unit charge. And here the charge is electrons. So electrons charge is just 1.6 into 10 raised to the power minus 19 coulombs. And the voltage here is actually 4900 volts. Okay. So the word that you can obtain from here is this. Okay. And to find out this energy, just let me multiply that. So it's 7.8 into 10 raised to the power minus 16 joules. Now, actually, this is the working of, I mean, this is the word done by the on the electron. An electron is moving, so this work will become equal to the kinetic energy of electron, right? Because this work is done by the very high voltage, 4900 volts. Okay, you see that uh, there is a very high voltage here, and that is 4900. And this 4900 is actually moving the electron to a very high speed. So actually, we are working on the electron to run and hit this plate with a very high speed to be detected as a light and diffract. So remember that when you move at a very high speed, like near to the speed of light, your particle nature disappears and your wave nature appears. Okay, and this is something that we are doing in this experiment. In this experiment, we are providing a very high energy to so that electron is moving near to the speed of light. And as soon as it gains that much of the speed because of the very high voltage, 4900, it will act like a wave particle. Okay, not it's like it will act like a wave, sorry, not a particle. So electron will not be electron anymore, it will be a wave. So when that wave hit the graphite plate, it will diffract just like wave. Okay, that shows that the particles do have the wave nature as well. So remember that this kind of experiment is actually an indication that the electrons, which is actually a particle, do have a wave nature, because here we are seeing the diffraction of the electron. And the diffraction is something purely related to the waves concept, not to the materials. Okay. So this work is actually done by the high voltage, and that will become the kinetic energy of the electrons. Okay. Of the electrons. So work is actually 7.8. Okay. And we need to find out the de Broglie wavelength. And from here, the velocity will be 2 into 7.8 into 10 raised to the power 16 divided by the mass of the electron is 9.1 into 10 raised to the power minus 31, taking the under root. And your V is 4.15 into 10 raised to the power 7 meter per second. Can you see? The speed is almost equivalent to the speed of light. It's very, very near, because the speed of light is 3 into 10 to the power 8, and it is reached up to 7. So now, because of this speed, you are able to find out the de Broglie wavelength using the formula of de Broglie wavelength. Okay, from here you're moving this way. De Broglie wavelength formula is lambda equals h over p, and p is actually m into v. So just 6.63 into 10 raised to the power minus 34, 9.1 into 10 raised to the power minus 31, into speed 4.15 into 10 raised to the power 7. And from here your wavelength is going to be 1.25 into 10 raised to the power minus 11 meter. Since your data is only in two significant figures, so your answer should be in two figures, significant figures as well. Three significant figures? No, just two significant figures. So 1.25 can be rounded off to 1.3 into 10 raised to the power minus 7. Okay, let me see the answer in the mark scheme. Okay, they have accepted it, but 1.75. Oh yeah, 1.75. It's not 1 point. It's not 1.25. It's 1.75. Yeah, sorry. So 1.75, and it should be rounded off to 1.8 because the significant figures in the data are 2. So I believe it will be the right way to mention this. Okay. Two. A student suggested that the beam of electrons would produce a diffraction pattern if a diffraction grating with 5,000 lines per centimeter was used. Okay. So this is diffraction grating, and this is the electron beam coming. Okay, deduce whether the second order maximum would be clearly visible on a screen. The screen is placed about a meter away from the diffraction grating. So this distance is 1 meter. And this is the central maximum. This is the, here you have n equals 0, or the central spot. Here the first maximum, here you have the second maximum, and so on. Okay. Similarly, here you have n equals 1, and here you have n equals 2. Okay. And we need to deduce whether a second order maximum would be clearly visible or not. Okay. Not that difficult. Just remember one thing. What is the wavelength that you have? Wavelength is 1.8 into 10 raised to the power minus 11 meters. Okay. Then for n equals 2 is the second order they're talking about, right? N equals 2. And the number of lines per centimeters, not per meter. So number of lines is actually 10 raised to the power 2 to convert centimeter into meter divided by, okay, just for now, write that as it is 5,000 lines per centimeter, and D, which is equal to the reciprocal of the number of lines. So it will be just 10 raised to the power minus 2 divided by 5,000. Now this 10 raised to the power 2 is to convert cm to meters. Okay, so that is the data you have. All right. So what do we need to find? First of all, write the formula for the diffraction grating, which is d sine theta equals n lambda. And from here, we are measuring the angle. Okay. So n lambda over d. So for example, if the angle is coming out to be just 2 degrees, so do you think the 2 degrees will fall here? Okay, this is the 2 degrees. So this 2-degree angle will not be able to cover second order or even first order clearly. For example, if the angle is 10 degree and it is just kind of covering the first order. So again, we will say that the second order will not be covered appropriately, right? So we just need to see where the angle is going to be. So from here, for the second order, just write 2. Wavelength is given as 1.8 into 10 raised to the power minus 11 divided by the distance, like d is 10 raised to the minus 2 over 5,000. Okay. So from here, sine theta is equal to 1.8 into 10 raised to the power minus 5. Okay. And from here, theta is sine inverse of this. Okay. When we do the sine inverse of this, the answer is going to be 0.00103 degrees. It's a very small number. So you just write as theta is very small. Okay. So n equals to will not be clearly visible. Okay. It's very easy. So this is just something that you're getting 0.0001. This is the angle you're getting. It's very, very small angle. So you're unable to detect the second order maximum, right? Okay. A student connected the circuit as shown. The battery has an EMF of 6 volt and the negligible internal resistance. State what is meant by an EMF of 6 volts. Okay. So EMF is actually electrons motivative force. Electrons are sleeping in a cable if you are not applying energy to them. So they will be all day sleeping just like me and you. So um, the battery comes in and motivates the electrons to flow and do some work. So we call the battery as EMF. Okay. And if EMF is motivating the electrons by giving them 6 joules of energy, so we will say that